In our last lessons, we solved boundary value problems by integrating Laplace's equation and applying boundary conditions. We computed resistance and capacitance from field solutions. Today, we introduce an elegant alternative, the method of images, which avoids solving differential equations entirely. The method of images was introduced by Lord Kelvin in 1848. The idea is beautifully simple. Instead of solving Laplace's equation with complicated boundary conditions on a conducting surface, we remove the conductor and replace it with an equivalent image charge. The image charge is placed so that the original boundary conditions are automatically satisfied. By the uniqueness theorem, this must give the correct solution. Consider a point charge q at height h above an infinite grounded conducting plane. The conductor enforces V equals 0 on its surface. We remove the conductor and place an image charge negative q at the mirror position, a distance h below the plane. This pair of charges naturally produces V equals 0 at the midplane, exactly matching our boundary condition. The solution above the plane is then just the superposition of two point charges. For the point charge q at position 0, 0, h above the grounded plane at z equals 0, the image is negative q at 0, 0, negative h. The potential anywhere above the plane is V equals q over 4 pi epsilon 0 times the quantity 1 over r1 minus 1 over r2. Here r1 is the distance from the real charge and r2 is the distance from the image. Below the conductor, V equals 0. On the surface at z equals 0, the induced surface charge density is rho s equals negative qh divided by 2 pi times the quantity x squared plus y squared plus h squared raised to the 3/2 power. If we integrate this over the entire conducting plane, we find that the total induced charge equals negative q. All field lines from q terminate on the conductor. This same approach works for a line charge above a grounded plane. The image is a parallel line charge of opposite sign at the mirror position. An interesting extension is the wedge geometry. When a charge sits between two conducting planes meeting at angle phi, we need multiple image charges. The number of images is n equals 360 over phi minus 1. This only works when 360 over phi is an integer. For example, two planes at 90 degrees require 3 image charges. Let's apply this to Sadiku's example 6.14. A point charge q is located at position A0b between two grounded conducting planes that intersect at right angles along the z-axis. One plane is y equals 0, the other is x equals 0. Find the potential at any point and the force on q. Step 1. Determine the number of images. With phi equals 90 degrees, n equals 360 over 90 minus 1 equals 3. So we need 3 image charges. Step 2. Place the images. We reflect q across each plane and add the image of the image. The 4 charges are plus q at A0b, which is our real charge, minus q at negative A0b, the reflection across x equals 0, minus q at A0 negative b, the reflection across z equals 0, and plus q at negative A0 negative b, the image of the image. Step 3. Write the potential. V at point px,yz equals q over 4 pi epsilon 0 times the sum 1 over r1 minus 1 over r2 plus 1 over r3 minus 1 over r4. Here r1 through r4 are the distances from each charge to p. Step 4. Find the force. The force on q is calculated using Coulomb's law with its 3 images. The image at negative A0b attracts Q in the negative x direction with a force proportional to 1 over 4a squared. The image at A0 negative b attracts Q in the negative z direction with a force proportional to 1 over 4b squared. The image at negative A0 negative b repels Q because it has the same sign. This repulsive force has both x and z components, with magnitude proportional to 1 over the quantity 4a squared plus 4b squared. Let's summarize the method of images. Replace the conductor with an image charge at the mirror position that maintains the boundary conditions. For a point charge Q above a grounded plane, the image is negative Q, and the total induced charge on the conductor equals negative Q. For wedge geometries, the number of images is n equals 360 over phi minus 1. The method gives exact solutions through simple superposition, avoiding the need to solve differential equations. In our next lesson, we'll move to Chapter 7 and begin magnetostatics with the Biot-Savart law.